Okay, we're going to look at a part of a 2011 question on standardizing with z-scores. We're only looking at part of it because we're not ready to do part A. So part A is not, we're not yet ready, but we'll be shortly. But for the time being, we're going to look at parts B and part C of standardizing with z-scores. So a professional sports team evaluates potential players for a certain position based on two main characteristics, which are speed and strength. Speed is measured by the time required to run a distance of 40 yards, with smaller times indicating more desirable or faster speeds. In other words, you want your time to be small, all right? You want it to small is faster. From previous speed data from all players in this position, the times to run the 40 yards have a mean of 4.6 and a standard deviation of 0.15. So here it is. There's our mean of 4.6 and a standard deviation of 0.15. With a minimum time of 4.4. We don't know what the maximum time is, but this was the fastest guy, all right? Fastest guy was 4.4. And by the way, I'm going to tell you real quickly that in this particular problem, it was not a normal distribution, all right? We'll talk about that at some other point, not in this video, but it's not a normal distribution. But we can still use z-scores even though it's not normal. Strength is measured by the amount of weight lifted, with more weight indicating more desirable or greater strength. So here we want small times and we want big strength, all right? And the amount of weight lifted has a mean or an average of 310 pounds and with a standard deviation of 25. Calculate and interpret the z-score for a player who can lift a weight of 370. Well, whenever we're doing z-scores, our formula is z equals x minus mu over sigma if we're working with a single score. So z equals x minus mu over sigma. Well, in this case, we know the mean, we know the x value, which is right here. So we're going to have z equals 370 minus 310 divided by 25. So in this case, we have z equals 60 divided by 25. And we end up finding that he's 2.4. I need to put this in context. My context is this. A player who can lift 370 pounds is 2.4 standard deviations above the mean player for that. Or he can lift 2.4 standard deviations more. He's 2.4 standard deviations stronger than the mean player for that position. And it'd probably be better if I had said 2.4 standard deviations stronger, because that puts it in context, than the mean for that position. All right, the characteristic of speed and strength are considered to be of equal importance to the team. So we don't have a preference. We say speed is important and strength is important, and we say they're equally important. Based on the information about the means and standard deviations of the speed and strength for all players and the measurements listed in the table below for A and B, which players should the team select if the team can only select one of the two players? All right, so let's talk about speed. We have 4.42 speed for player A and 4.57 for player B. And we know that the mean is 4.6 and the standard deviation is 0.15. So the mean here was 4.6 and the standard deviation happened to be 0.15. When it came to strength, and I'm going to use a different color, I'm going to use blue. When it came to strength, we had a mean of 310 and a standard deviation of 25. So what I'm going to have to do is I'm going to have to calculate z-scores for each of these. So on speed, player A. So I'm doing player A. So player A is here, and I'm going to do speed and strength. So when I do player A for speed, it's 4.42 because that's their speed minus the average divided by the standard deviation. And I find out that he's 1.2 standard deviations faster. All right. And then I go do the strength and I go, well, all right, his strength. He lifted 370. The average lift was 310 with a standard deviation of 25. So he's 2.4 standard deviations stronger. 1.2 standard deviations faster and 2.4 standard deviations stronger. When I go to player B, it's like 4.57 was his speed versus the average of 4.6. So he's 0.2 standard deviations faster. And when it comes to strength, 375 minus 310 is 2.6. So he's 2.6 standard deviations stronger. When I look at this, it's like, you know what? A is faster than B, but B is stronger than A. So who should I be choosing? Because they say they're equally. Well, player B is slightly stronger than A when I look at their z-scores. In other words, a 2.6 versus a 2.4. However, player A is substantially a full standard deviation faster than player B. So this is only 0.2 standard deviations stronger. This is 1 standard deviation faster. Relative to the other players, I'm choosing A because he's a full standard deviation faster than B and only 0.2 standard deviations less strong. All right. So I choose player A because he's a full standard deviation faster than B and only slightly less strong, and both strength and speed are equally weighted. This is the important statement because I had to show my math. All right. I had to show my math, and then I have to make a decision. And this decision should be phrased something along those lines. I should be also saying what all this means. Having a calculation with no meaning helps. Is not good. So I have to give some meaning. Player B, slightly stronger than A and is able to lift 2.6 above the mean. Player A is substantially faster. I would choose player A. Why? He's a full standard faster than B and only slightly less strong. And they're equally weighted. This, I have to have that part that I boxed off. Hopefully that helps. Thank you for watching.